Hello, Mr. Kramer. Let's see if we can get this focus a little bit better here. That may be the best we get. Guess the other option I have is let's see if that might work a little better. Only downside here is you get reflection of the screen. Bet y'all may have to deal with that. I think that's a clearer. Is that clearer for everybody? You're muted. Let's get the chat up here. Okay, it looks like people are having trouble with the link. There was a let's see if I can send an email out real quick to everybody. That's only to me. Let's see, Sim. Let me see if I can get that correct link here. Okay, it looks like we had some trouble with the link that got sent out, so I just sent out an updated copy of that link to see if we can get a few more than 2 people in here before we get started. There was a third. All right, that's 4. Let me get this centered back on the whiteboard for us for module 14. Good enough. Wish there's a way I could stop that glare a little bit. Wait, let me turn my screen brightness down maybe. It's not working. Oh well. We'll deal with what we can deal with.
Good.
All right, I unmuted everybody. How's everybody doing?
Doing pretty good.
Good.
I'm fine.
Really visible there. We hold nothing to the new normal. I mean, we're homeschoolers. It's not like we didn't already self-isolate, right? So we have a fairly long chapter. I guess I'll go ahead and get started for it's being recorded, so hopefully people can get it on the YouTube link that didn't see the email with the updated link for today's class. Let's see, how am I going to do this? I'm going to get myself situated here. I did finally, just today, actually find a great way to maybe be able to type in equations. So I might see if I can get a slideshow style of thing working by next week. We'll see if that happens or not. So just to get started, we are on to module 14, electric potential. We've learned about electric fields, electrostatic forces. Now we can learn a little bit more about how things start moving. So everything was very static before in the previous chapter. We're now going to unpin them and kind of let them start moving, let them start doing their thing and behaving to things. So the first thing that we are going to hit is electric potential. And I'm going to kind of harken back to earlier chapters when we were talking about gravitational potential energy, where you take an object, say, let's take a ball and roll it up a hill to the top of a hill. You have you've done work, you've put energy into the system. It's now sitting at the top of the hill. If you let it move down, that potential energy will turn into kinetic energy and start moving. Fairly similar concepts here. So if you've got that stuff, you should be good here. It's just a slightly different flavor on it. So if we, you know what, I'm just going to go quick. You guys can read the book. I'm not going to read through the book for you. So I do definitely recommend reading the chapter. It's a good thing. So the first thing we're going to talk about is, so I'll hit the highlights. Electric potential. And we get an equation for this. We're going to call the electric potential V. And that'll make a lot more sense in a little bit. And that's going to be equal to this K constant we've been using, the 9 times 10 to the 9. Newton, what is it, meters squared per coulomb squared. And then the charge that is generating this electric potential, so the size of the hill, so to speak, and then divided by R. Okay, so the distance we are away from this thing that's exerting this force upon us. So V is the electric potential, K is that Coulomb's constant that we've used before, Q is the magnitude of the fixed charge, and R is the distance between the fixed charge and the moving one, or the other charge we're dealing with. So what units are we working with here? Well, let's take a look. That's going to be K is that Newton. Ooh, that does not look like an N. That's better. Meter squared per coulomb squared. So that's the K. We're going to times it by a coulomb. That's still on the board. Good. And distance is going to be measured in meters. So that meters and that meters is going to cancel one of them. That coulomb is going to cancel one of those. So the final unit we're going to have is a Newton meter per coulomb. Let's see, that's mostly out of the glare, it looks like. Cool. So we can rewrite this a few extra ways. It's not an energy unit. So a Newton meter is a joule. So that's energy. So this is energy per coulomb. So it's not quite potential energy. So, you know, be careful with that one. So be aware of that. Electric potential is not potential energy. We can get to potential energy from it, but it in and of itself is not potential energy. It is just a potential. So despite the confusing terminology there. And what we're going to take this, I'm going to come right up on the side here. So this Newton meter per coulomb, we have given it a name. We're going to call it the volt. That's why we have a V for electric potential. So volt is a Newton meter per coulomb. That's the unit we're going to be using for our electric potential as we keep going. When we are using this equation, also, the other thing to be aware of is use your sign on the charge. It will make a difference whether it's positive or negative. Basically, are you rolling it up a hill or rolling it down into a trough is going to be kind of mentally the way you can look at that. Whether it's positive or negative is going to make a difference. All right, so we can do a quick example problem on this one. We have, I'm just doing example 14.1 here. Consider we have a plus 3.2 millicoulomb positive charge that cannot move. So our charge is plus, what was it again? 3.2 millicoulomb, which is 3.2 times 10 to the minus 3 coulombs. Readable, that's readable. That cannot move. What is the electric potential 45 centimeters from the charge? So R, the distance is 45 centimeters, which is going to equal 0.45 meters. Again, very first problem of the chapter, it's just going to be a straight application of the equation. So we're going to have the, what's the electric potential? All right, so we've got all our stuff kind of blocked out here on the side. We're ready to start working the problem. I'm gonna, I can't really slide this over. I will slide over. So we start with our equation that we know we're gonna end up using because it's got everything in it that we have and everything in it we don't have. So that's obviously the equation we're gonna use. It's also the only one we've given you so far, so that makes it really easy at this point in the chapter. So that's going to equal 9 times 10 to the 9th Newton meters squared per Coulomb squared times, and never forget the units. If for nothing else, it will help remind you that you've got meters here and centimeters here. If you forgot to make the conversion early on, it'll help you remember what conversion you need to put there. Q is 3.2 times 10 to the minus 3 coulombs, over, not ready for that yet, 0.45. Notice that's not meter squared. This is not inverse square law. It just goes linearly inverse to the distance there. We plug this into a calculator, and I'm just going to read this one out of the book. So if someone wants to plug in the calculator, make sure the book got it right. That's an amazing thing. The electric potential is then 6.4 times 10 to the 7 volts. And so we have our answer. We will box it in so that the grader can see it. So again, working a problem on a test, bring everything out to the side, make sure you've got your equation, plug it in, and then get your answer. I was helping a particular parent on Tuesday night. Again, remind your parents, 7 o'clock on Tuesday nights. I'm trying to make myself available on a video chat like this to help any of your parents that are having problems with grading these tests. A particular student had, let's see, they got everything out here. They got the equation right. They plugged all the numbers in, but they got a wrong answer here. And then there was another part to the problem where they did everything right except one little thing. But because that number was in here, it got wrong. You know, all of that was kind of wrong. It did not match the solution of the book, let's put it that way. And then the final answer at the end was also not correct because of that. Well, in reality, the student got everything correct, except somehow there was a calculator error or something here. Everything was set up properly. It just spit out the wrong number. And then in the second phase of the problem, there was one mistake on how to do things. And so for a 3-point problem, instead of basically missing a half a point here, a whole point here, and a whole point here, and missing, 2.5 out of 3 out of the problem, I think they probably missed about a half of that because, you got to knock something off if you can't work your calculator and a little something off because it was with a degrees calculation, if I remember correctly. But the physics and the understanding of how to work the problem, I believe, was fairly intact in the head. So that's where we're working on things there as well. So this is kind of a little note to the parents too, if they're watching these videos afterwards as well. Where's my eraser? There's my eraser. So that's a quick example of how we use this equation. Moving right along, we're going to move to electric potential, potential energy, and potential difference. So we potentially have a lot of potential words in our vocabulary for this potential chapter that might potentially be on a test if you catch the potential humor in the situation. So electric potential is not potential energy. How do we get to the potential energy? Well, glad you asked. First of all, let's take a look at, what was it? A volt was a Newton meter per Coulomb, which is the same. A Newton meter is a joule. The book does not cover this particular. So really we've got a joule per Coulomb. Joule is a unit of energy. Therefore, in order to get this into energy, we're going to have to multiply it. I'll do this. If we multiply it by Coulomb, then those would go out. We'd end up with joule. All right. So our equation for potential energy, electric potential energy, is going to be this electric potential, which we measure in volts, times the charge, the little test charge, the little ball we roll up the hill. So electric potential, just the V, is telling us about the hill. Q is telling us about the size of the ball that's rolling up a bit in this analogy that we're making up in our heads here. And so this is another equation that you'll want to have down, is the electric potential energy is the electric potential times the charge. Actually, I think the book has it written, not to confuse anyone, Q times V. I don't really care. So we're going to keep going. Actually, just had a thought for those of you, another way, not in the book again, but that might help you kind of make this analogy between gravitational potential energy and the electric potential that we're doing right now is gravitational potential energy is mgh. So that's the ball. G is gravity, h is the size of the hill. Well, our electric potential is K big Q over R, right? R is the distance away we are, which is kind of like the height that you go up the hill. So KQ is really kind of like our gravitational constant, right? So if we go electrical potential energy, and we know that that is Q, which is the size of the little test charge that we're measuring on. Well, that's kind of like the ball we're rolling up the hill, so that's good. So all of this is like the G and the H. I would say it's kind of like KQ times, and then the 1 over R is kind of like the H. The closer you get, though, the more
Do I?
You what? Hello? Was there a comment, question? Cool. Okay, so this is how those equations would kind of line up. These are the constants. This is the size of the hill, so to speak, how big the charge is, and the Coulomb's constant we have. That kind of goes into the constant there. And then the hill, the height that we're up the hill is kind of the 1 over R. It's kind of an inverse thing. So farther up the hill you are, the closer it is that you get. So again, that's a freebie. That's not in the book, but if that helps maybe cement some of the concept of what we're doing with potential energy here to something you've already got, that should be good. All right. So moving right along, potential energy, we've already done that. Awesome. Now we talk, so we've got electric potential, we've got potential energy, and now we're going to move on to potential difference and the change in potential energy. All right. So clearing our board off for us. Make sure we've got it all covered. Okay, so what's the best way to do this? We've got our test charge Q right here in the middle. Or sorry, the static charge. And we've got our little test charge, little Q out here to the side. As this moves around, depending on whether it's positive or negative, it's going to either be attracted to or repelled by. That force is going to get stronger the closer it gets, etc. How's the potential energy of this going to change? Which later we'll probably get into some velocities, right? Well, if we're talking a change, or let's do it this way. We know our potential energy equation is Q times the electric potential. Well, if we want to get the change in potential energy, it's going to be the change in all of this, but this little charge isn't changing. The only thing that's changing is the electric potential as it moves around in different places. So that's going to be Q delta V. Just stepping us through it here. Actually, that's the next equation. So potential difference. So the change in potential energy is determined by the change in the electric potential. The charge is the same. The electric potential is what's going to change. Therefore, it's the change that, so this is also the difference in electric potential. All right. Let's work a quick example problem on this one too, just to kind of see how this is going to work in reality. So if you've got how, you know, if this is R and then this little thing, let's move it out here. And now we have a new R, R2. It's a different R, so that means V2 is going to be different than the V right here, just because we're in a different location. Everything else staying the same. With the equation, yeah, I know I'm repeating myself here, but K, Q over R. Well, K is staying constant by default. Q hasn't changed. R is changing, therefore V is changing, therefore that's changing, et cetera, et cetera. We can come up with some great equations to deal with all of this, should we ever want to. So the problem, we've got a charge that's free to move, placed 68 centimeters from a fixed charge. If the freely moving charge moves 15 centimeters towards the stationary charge, what's the change in potential energy? And did the potential energy increase or decrease? So let's actually work that specific equation. Let's draw it out first, then we'll label everything out. So we've got a fixed charge, Q. That fixed charge is plus 4.8 millicoulombs. 4.8 millicoulombs. We have a, let's see, minus 5.6 charge. So we've got another charge that is minus 5.6 millicoulombs. And it is 68 centimeters. 68 centimeters from it. We then move that charge, the little charge, 15 centimeters towards it. So that's going to move in, and it's now going to be here. That is 15 centimeters closer. So I'm going to go ahead and do that math and say that's 53 centimeters. Okay, everything else staying the same. And we want to know what's the change in the potential energy. So right here, delta PE equals question mark. All right, so let's label this all out. So we've got a Q, which is plus, and I'm keeping the signs in here because they are important, millicoulombs, which is a plus 4.8 times 10 to the minus 3 coulombs. I would highly recommend specifically doing this. Don't just do the shortcut and write this thing down. That's not necessarily for your good. That's for your parent who's grading this good. There was one step in one problem I saw that the parent brought to me where it was like over R squared, and the student just went ahead and squared the R and put the number in instead of showing it squared and taking the step. So we had to kind of backtrack to figure out, okay, where'd that number come from? Oh, that's that number squared. They're good. But it was extra work for us, and you know, parents are lazy. We don't like extra work. So there you go. We've got, let's see, Q is going to stay the same. Q is minus 5.6 millicoulombs, which is minus 5.6 times 10 to the minus 3 coulombs. We've got an R1, which is the first R, which is 68 centimeters, which is 0.68 meters. And we have an R2, which is 15 centimeters less than that, which is 53 centimeters, which is 0.53 meters. All of that is hopefully still legible. I keep looking back for the chat. If someone is saying something in the chat, please like unmute and speak up, because I'm looking at the board more than the computer screen right now. Where are we at? Oh yeah, doing the problem. What is the change in potential energy, and then does the potential energy increase or decrease? All right, so you know, one way to, we can do this two ways. We can do this as the direct, what's the change in potential energy, or we can calculate potential energy before, potential energy afterwards, calculate the difference, and then we'll be able to answer the second question a lot easier, which is, I think, the way we're going to do it. So we want to know the change in potential energy. I like to block that off because it lets me know what I've got, and I can go look at it really quickly on the page, and your parents can as well. All right, so potential energy beforehand. I'm going to label that 1. that is going to be equal to, what was our potential energy equation again? It was Q delta V, right? Actually, hang on a second. Whoops. I have a very little shelf here, as you can tell by what my backdrop is. Nope, that's changing. Is this going to be QV? Well, we don't know what V is, so we're going to have to expand this equation out because we also know, well, let's see. We know that, I'll put the equations down here that we're going to use. QV, we also know that V is K big Q over R. So that means that this is going to be K Q big Q over R. Ooh, that looks really suspiciously like something we've seen before. Except there was a square, I believe. So this is rewriting it. K big Q little q over R1, because it's a PE1, all the rest is the same. That's going to give us 9 times 10 to the 9th Newton meter squared per Coulomb squared times, ooh, this is not going to fit on the board. I'll write it down here. 9 times 10 to the 9th Newton meter squared per Coulomb squared. That's K. Big Q is plus 4.8. I'm going to put that explicitly in there so I know that I've written a positive charge. I highly recommend you do the same on your test or problems you work. Little q is minus 5.6 times 10 to the minus 3 coulombs divided by R1 is 0.68 meters. That means potential energy 1 is going to be, and again, I'm not going to take the time to plug it into my calculator. If someone else wants to do that and make sure the book got a right number, that would be amazing. KQR. Oh, wait a second. Okay, I think the book is asking a question it's not meaning to ask. The book asks what the change of potential energy is, and then they're calculating the potential. I'm going straight to calculating the potential energy. So I am going to actually work this different than the book. I already have started, so I'm going to plug it in my calculator here. Oops, hang on a second. Let's see. 9E9 enter 4.8E minus 3 times 5.6E minus 3 times, and then 0.68 divide. I am getting 3.55, which would make that 3.6 times 10 to the 5th joules, right? Joules. It's potential energy, so it should be. Newtons, let's cancel the 2 coulombs, cancel a meter, we'll end up with a Newton meter left. Yes, okay, awesome. So potential energy 1 is that. I'm gonna store that over here because I need that board space, times 10 to the 5th joules. So that's the initial potential energy. We do it again, and I'm going to cheat here. This is potential energy number 2 is going to be K. That was V1. Now it's going to be V2, which is going to be over R2 is the only change there. And then C3PO will answer the rest of the question for those that got that. R2 is 53, so that's 0.53 meters this time. 5.3 divide, and I believe that will come out as 4.56 rounding up to 4.6 times 10 to the 5th joules for PE2. Okay, so we see that the potential energy increased from 1 to 2, and it increased by 1.0 times 10 to the 5th joules. So the change in potential energy, oops, hold on a second. Actually, let's double check. This was actually minus, because we had a minus sign here. It was also a minus sign, so it'd be a minus sign here. So it actually went from minus 3.6 to minus 4.6. So that would actually be a decrease. No, hang on. It got bigger, but it's in the minus. Potential energy. Hold on a second. I'll get this one. Yes, that is a decrease. So the potential energy decreased because this minus that is going to be a minus 1.0 times 10 to the 5th joules. So that's the actual answer right there, is that the potential energy changed by minus 1.0 times 10 to the 5th joules. Therefore, it decreased. Okay? Because the change is negative. And that's where the sign is important, and making sure things are right is important. So final minus initial gives you the change. So minus 4.6 minus a negative is a positive. So plus 3.6 still leaves us with a minus 1.0. Just to make sure all of that is clear, because just like in grammar and English, you put too many double negatives in there and you have to figure out what the sentence actually says. Try talking to politicians. Okay. I think we probably went over all the stuff here. Okay, so I actually went straight to the potential energy. They did not do that. They actually calculated the change in potential first, and then they multiplied in the Q to get the potential energy. There is value in doing that. The value is the change in potential. So if we had basically left off Q off of all of these, if we had done Q delta V, and then we said delta V is really going to be that equation there, we would have had two potentials, and then we could have found the change in potential and multiplied in the little Q at the end. Where is it? Yeah, we could have multiplied in the Q right there to that delta V to find out. The reason why it's useful to go to the change in potential energies is because we can then do things like batteries. You've got a standard, C cell or D cell battery that goes in a light bulb or a flashlight or a radio or something like that. And it's going to be measured in like 1.5 volts. Well, that 1.5 volts is actually a change in potential across the battery, change in electric potential. Hold on a second, and I will get a nice visual picture here. So we have a battery with a little nub on top. That's the positive end and that's the negative end, right? Now it should start making sense why a battery has a positive end and a negative end. If this battery is rated at 1.5 volts, then what it's really saying is that the change in potential is 1.5 volts from here. Let's draw an arrow. There we go. Arrow works. To here. So top of the hill, bottom of the hill. That's the way I remember which side of the battery is positive. It's got the little hill right in the middle of the top center of it. That's the positive side. And so top of the hill, bottom of the hill, the electric charges, electricity actually flows that way. If we picture them as positive, they'll go the other way. And when we get to circuits, we're going to do some funny stuff, which will totally turn a lot of this on its head. But you need to know this before we can get to there. Everybody doing okay here? Let's see. I'm seeing being. Yes, yeah, okay. All right, y'all joking around the chat. That's cool. Make sure there weren't any questions I needed to answer. And so learning about potential differences is useful. Now, one other value that we need to learn about right now is the electron volt. It is abbreviated little e, capital V. Hope y'all can see that yet out of the glare. An electron volt is defined As the amount, the decrease in potential energy when an electron moves through a potential difference of exactly 1 volt. So if I had, what's the best way to do this? Well, doesn't matter. If I take something that's, let's say a 1 volt battery. I don't think we have 1 volt batteries, but if we have a 1 volt battery, and I take a little electron that has negative charge on it, minus 1.6 times 10 to the, I forget, is it minus 19, I think, coulombs? Anyway, we take an electron and we move it to a new location or across a potential difference of 1 volt, then that is defined as an electron volt. This will come in handy as we start dealing with circuitry, subatomic particles, et cetera, et cetera. This concept is used in a lot of places in particle physics, for instance. And so it is a charge. If you look at it this way, it is a charge, little q, that is being moved across a potential difference of 1 volt. Let me see. So if we have the charge times the initial voltage and that same charge times the final voltage, and that final voltage is 1, well, that is Q times a delta V, right? Q times delta V is potential energy. It's an energy form. So this is a unit of energy. I don't know if any of y'all have heard these in the news or whatever, but a particular part accelerator is sometimes called a tevatron. Well, that is a basically it's a trillion electron volt cyclotron. So it actually accelerates, it pumps a trillion electron volts of energy essentially into a subatomic particle, speeding it up to near the speed of light before it slams it into something else and see what parts fly out. It's kind of like taking two really finely crafted Swiss watches, smashing them together, and then looking at all the pieces that come out and try to figure out how they were put together to start with. That's pretty much how all particle accelerators work, is you smash things together and see what comes out. Electron volt, great, we got that. Moving on. Conservation of energy in an electric potential. So yes, we have it. Energy is always conserved. Unless, of course, you destroy matter and turn it into energy. But I like to think of matter as crystallized energy, so energy is always conserved. So we've had this before when we were dealing with the potential energy to kinetic energy. We dealt with the conservation of energy. In those situations, it happens here as well. So let's do an example problem. It'll make a lot more sense seeing it in effect. So what we've got is a freely moving particle with a certain charge is placed a certain distance from a fixed charge. The particle starts at rest, and it's going to start moving. Now, when it moves to a different distance away from the fixed charge, how fast is it going? So let's draw the thing here. We've got our big Q here in the middle, which is minus 2.0 coulombs. Minus 2.0 coulombs, all right? We put a particle 13 centimeters away from it. So let's do it on this side. We put a little charged particle Q there. That little charged particle Q is minus 15.1 millicoulombs. Minus 15.1 millicoulombs. We'll have to do a change there. And that is 13 centimeters. Now, that charged particle actually has some mass. Ooh, it's actually relatively large. So let's make the mass 2.34 kilograms. All right. So we've got a charged particle that's got some mass a certain distance away from here. Now, because these are both negatively charged, we know they're going to repel each other. Now this one we're not going to allow to move, so this one is going to be accelerating away. After a certain amount of time, it is now, I think it says 95 centimeters away. Let's do it down here. 95 centimeters away. And we want to know how fast it's moving. So it's starting at rest. It's not moving. We plunk it down right there, not moving. We let go. They start repelling away, and that thing's going to go pew like that. How fast? What's the velocity there at the end? I hope some of you are already starting to see how this works based on our like dropping balls and things like that that we did way back before on kinetic energy and potential energy and energy conservation. So first, let's get things down. We know that Q is minus 2.0 coulombs. We know that little q is minus 15.1 millicoulombs. Let's go ahead and convert that to minus 15.1 times 10 to the minus 3 coulombs. We've got a, let's go ahead and put the mass up here because it's not changing. Mass is 2.34 kilograms. And we know that the initial distance is going to be equal to 13 centimeters. Again, let's convert that for mom and dad who are grading this to, let's do it right, 0.13 meters. And we know that R2 is going to be equal to 95 centimeters. Again, writing it down the way it was given and then converting it. I get how much of a waste time that means, but those little details mean a lot when you're doing it early on here. We want to know what is the velocity. Actually, let's be a little more explicit. We know the initial velocity is 0 meters per second. We want to know what the final velocity is at the end. And we'll box that off so we know that that's stuff that we're not going to mess with anymore. So what do we have? Just generic thoughts before we really actually start calculating on the problem. We know that total energy before is going to equal total energy at the end. Initial with a 0, F with a for the final. We know that the total energy is equal. Wow, what am I writing? Is equal to the potential energy plus the kinetic energy, and that's going to equal to the initial. And that's going to equal the potential energy final plus the kinetic energy final. All right. Well, at the beginning, we know that the kinetic energy is 0. So we're going to go ahead and simplify some things. So all the energy at the beginning is just potential. At the end, we're going to have potential plus kinetic. So let's see what those equations are. We know that, actually, you know what? There's a couple of ways to go about this. I'm going to do what to me seems a little more simple, realizing there are other possibilities. We could just go ahead and calculate that, subtract all the numbers around. I'm going to see if I can make it a little simpler. It may not work, but let's see how it goes. We know that the kinetic energy has the velocity that we really want to find out. So I'm going to flip this around first, and I'm going to say that the kinetic energy final is equal to the potential energy initial minus the potential energy final. I hope everyone followed that. So I subtracted potential energy final from both sides, and then I just flipped it around the equal sign. We know that this is going to equal 1/2 mv final squared, which is the number we're looking for, is going to equal the initial potential energy. What's the initial potential energy? It's going to be, and I've erased all the equations, I just want to make sure I get the right one here. Potential energy is going to be, remember, Q times V. So that's going to be Q V naught minus Q V final, where V is the electric potential. I can simplify this a little bit by pulling that Q out and make V naught minus VF. It's still visible. That is still visible. Cool. Get out of my chair, get down on the floor where I can actually reach things. Well, what is V naught over here? V naught is KQ over R naught minus KQ over R final. I can simplify this out a little bit, and I can say this is, I'm going to pull the KQ out of both sides. So I'm going to have Q, actually, let me rewrite this a little bit. K, Q, Q times 1 over R naught minus 1 over R F. That's just reverse distributing out of the equation. There, a little algebra for those of you that have had it. This again is going to equal 1/2 mVF squared. Whoops, squared. I'm going to have to erase and start moving back up to the top again. So bear with me here for a second. I'll leave the bottom one and move from there. Limitations of a small screen. There. I'm actually going to get rid of that too. So taking this, coming back up to the top, if I multiply by 2 over m on both sides, that'll cancel those. So I'll end up with Bf squared is going to equal 2 k q, little q, over m times this 1 over r naught minus 1 over r f. Hope everyone's following. To get rid of the square, we can just square root both sides. Make sure that's not confusing there. Looks like a bit of a nasty equation, might kind of be, except we now have everything in. We can plug our numbers in and get our answer. So I'm going to start way over here because this is probably going to take me some space. Square root of 2 times 9 times 10 to the 9th. I also want to make sure that all of our units work so that I didn't screw something up. So I'm going to leave them in here. Newton meters squared per coulomb squared times K, that is K, Q minus 15.1, no wait, oh yeah. This is not proper scientific notation, I get it. It doesn't matter when I plug it into the calculator. Times 10 to the minus 3 coulombs times Q, oops, I did this reverse. Let me do the big Q first, just so we've got them all in the same order. Minus 2.0 coulombs times minus 15.1 times 10 to the minus 3 coulombs. That's all the K's. Q's over M, which is 2.34 kilograms. And then all of this times 1 over R naught, which is 1 over 0.13 meters, minus 1 over 0. What was it, 95? 95 meters. And that whole thing square rooted. So we do all the math there, and we're good. Obviously, order of operations, I'm going to do that first, and then start multiplying everything and then divide things. Let's check what we've got on units first, though, before I plug this calculator and make sure I didn't waste all my time plugging into a calculator. So I've got meters here. All right, and even though it's minus meters, we're going to have meters on the bottom, meters on the top. So the meters are going to cancel one of those. Coulomb, coulomb, coulomb squared, we're going to cancel all of that. Great. So we're going to end up with, and I'll write it over here, Newton meters per kilogram. Yep, that's it. Well, that's really weird. Oh, wait, but a Newton, we have to remember what a Newton is. A Newton is a kilogram meters per, I'll write it on the bottom, meters per second squared. We're going to multiply by meters, divide by kilograms. So the kilograms cancel. We're going to end up with meters squared per second squared. But we're doing a square root over everything. We'll end up with meters per second, which is a velocity. Yay, my formulas were probably correct. Not a guarantee, but at least I guarantee they weren't wrong that direction. If I'm wrong in some other weird way, and I got to find my calculator. All right, so we have 2 times 9 times 10 to the 9th. We have minus 2. We have minus 15.1 times 10 to the minus 3. We have 2.34 divide. Oh yeah, we forgot to do the other one first. 0.13, 1 over 0.13. Where's my 1 over? There's my 1 over. We have 0.95, 1 over that. Subtract that from that. And oops, I think I may have, let me go ahead and put it back in. 2 times 99 times minus 2 times minus 15.1 times 10 to the minus 3 times and 2.34 divide. Ooh, that's a larger number than I was expecting. Oh, maybe not though, because it's a tiny little, well, let me double check. I plugged that in my calculator right, because I'm thinking I may not have. Next page. Oops. Calculator turned off. Okay, nope. And then square root. It was a square root I forgot. Cool. I'm good. Let me find my eraser. So I ended up with 3.92. How many sig figs do we have? 3, 3, 2. I'm going to go with 2. So that's going to be 3.9 times 10 to the 1, 2, 3, 4th meters per second. And I believe the book actually ends up with a slightly different answer. They end up with 3.9 times 10 to the 4th. Awesome. So we got what the book answer got. Yay. We're either both right or we're both wrong. I'll go with the former because it makes more sense to me. Do we have any questions on all of this so far? All right. Yep. Just jokes. Bad ones. I got it. Bad jokes are the best type, because they eventually grow up to be dad jokes. Of course you did. So fairly similar to what we've done before. Potential energy, kinetic energy. We just have a different equation for potential energy. What else we got? Other problems similar to that. I won't work through those. I'll leave those for you. Capacitors. Next thing we have to deal with is capacitors. Unfortunately, doing a lab here, I've still got to figure out how we're going to make that happen. The lab that's in this book that kind of covers this section is actually fairly easy to do if you've got like a styrofoam disposable plate, like paper plates, but styrofoam ones work better, and aluminum foil at your house. You can probably make this next one work. It is definitely worth trying to put together to do. Capacitors are a way to basically store charge, to store energy per se. Actually, we're storing charge, not energy, but it works the same way. A lot of you who might be like audiophiles or car people that like to have the big thumping bass in your car may have capacitors in there, big, large capacitors in there. Those are needed because they store up the charge for those that high current need that you're going to have. A capacitor is in some ways similar to a battery. In a lot of ways, it's completely different though. Capacitors can deliver charge much more rapidly. They can charge up much more rapidly than a battery can. They, however, in the real world, don't tend to hold their charge for quite as long. So they're much faster acting, let's put it that way. And so basically, to make a capacitor, the easiest form, the earliest form that was made were what are called parallel plate capacitors. So let's say we have two conductors on the side, and we have a wire that attaches to the circuit, to a battery, to whatever. And those are metal plates. So if we end up with, let's put a whole bunch of electrons on here. They're going to flow across and put a whole bunch, I hope y'all can see that, bunch of negative charge on that top plate. Well, they're not conducting. There is no touch. There's an air gap between these two plates, or a foam gap, which is really just air with other stuff in it. There's an insulating gap here, so the charge cannot flow directly from one side of the capacitor to the other. But we can charge it up by putting a whole bunch of charge on one side, and then by the process of, anybody want to type it or say it, what's the process? What's going to happen when a whole bunch of negative charge is this close to another place where the charges can move freely? This was from the last chapter. You rub up a balloon, you put a whole bunch of charge on one side. What's going to hit us on the other? Induction, yay, good job. And so by induction, all the minus charges are going to go booking and fleeing because they're going to get pushed away. And what's going to be left is a whole bunch of positive charge. All right, I'll get away from my running away. Run away! Brave, brave Sir Electron. He bravely ran away. And you're going to have a bunch of positive charge here. Well, we now have a situation where we have a bunch of negative charge here, a bunch of positive charge here. We're going to have electric field or an electric field in between these two parallel plates. Now, these are usually very, very close together. And so with that, we're going to end up with an electric field. Now, electric fields go from the positive to the negative, right? So the arrow lines I will draw will be like this. So the electric field in this parallel plate is going to end up pretty well defined. It's going to be a whole bunch of fairly straight lines. And the big thing on a capacitor is it's the size of the plate versus the gap. Those are the two dimensions on a capacitor that really kind of make a lot of difference. And so you want this size to be as big as it can be compared to how big the gap is. So if it's a smaller capacitor, that gap has to be much smaller. Out of the sides, real world, not what you're doing in class, but these are going to start kind of curving like that. And you're going to have, some field out like that that gets a little harder to calculate. We're not going to worry about those. In the real world, that's why we make capacitors bigger around than the layers are thick in between. So we don't have to worry about the weakness of everything in the middle. What happened? A little terminology. We're going to get this from the lab that we're not actually going to do. Actually, you know what? I think y'all should be able to do this lab. I will say this much. Do lab 14.1 at home. If you cannot find two styrofoam plates, paper plates will work almost as well, but styrofoam are better. Aluminum foil, tape, scissors, paper clip, and a balloon. Then have your parents send me an email. All right? Fair enough? Cool. I think most houses probably can find something along those lines. If you can't find the styrofoam or the paper plates, you could probably use some fairly thin corrugated cardboard. Basically, nope, we're not going to help you behead your brother. But we will teach you how to build a capacitor that you can shock him with. Does that work? Cool. So, thin layer of corrugated cardboard would work as well. Potentially several sheets of notebook paper could work as well. It just needs to be about that thick, non-conductive. So you can actually try some different materials and see if you have different effects as well. But let's go ahead and say 14.1. I think that's one that can probably be done at home. I'll tell you a little about what we're doing. The styrofoam plate or the cardboard or the paper plate or whatever you put in between, the insulator, is typically called a dielectric. Make sure I spelled that right. So a dielectric. All right. It's typically called a dielectric. So that's just the terminology that we'll need there. Little bit on there. Yep, you're going to bring the balloon up close. You're going to charge up the foil. So essentially what you're going to do is you've got those 2 sheets of aluminum foil over the paper, styrofoam plate or whatever, paper clip coming off. You're going to charge it up by rubbing the balloon, creating charge, touching it to the wire over here so that the charges will all build up on that plate. Rub it up some more, charge it up, rub it up some more, charge it up. Keep charging it up. When you're finally done charging it, you put the balloon away, placed one hand on the foil strip. With the other hand, you touch the paper clip. At that point, you should have felt a jolt of electricity. So if the room is dark enough, so essentially you're going to make static electricity just like rubbing your feet up on the floor and then touching a thing, but you're going to be storing up charge in here. So I'm sorry we didn't have this class before yesterday. It would have made a great practical joke to be able to charge up and like charge an electric door handle to shock someone with. I will leave it up to you and your parents on whether or not April Fool's Day gets extended through the weekend for you. Oh yeah, electric field. Okay, yes. Oh, hey, look, they drew the nice same picture I did. The electric field is fairly easy to calculate electric potential because it's all just these straight lines. You got the gap there, all these fixed values. And so the electric potential on a capacitor, where's the best place to write it? Let's write it over here. The electric potential is going to equal Q over C, what's up there? Oh, yeah, C sub Q. V's electric potential. Q is the total amount of positive charge stored on the capacitor. And CQ is called the capacitance of the capacitor. So, trying to think the best way to go with this. So they're called capacitors. We talk about a value called capacitance. Basically, this comes out of the old original discovery of this stuff. It still holds true, but these had the capacity to store charge. So they were capacitors. They have a capacitance that determines how large their capacity to store charge is, if that makes sense. Because at some point in time, the charge gets so great that it's gonna arc across. Even though you've got an insulator in there, it can short circuit through the capacitor and do bad things. Never overcharge capacitor, or you won't have a good capacitor at the end. Even if it's a flux capacitor and you charge it up with 1.21 gigawatts or gigawatts, sorry, he likes to call them gigawatts of power. Depends on whether you're British or not. So we have this value that is just a definition of the capacitor, and we say it's the capacitance. It involves a lot of the physical properties. How far apart it is, what's in the middle, how big or round it is. All of those various factors goes into how much charge does this capacitor have the capacity to hold? What is its capacitance? And so this equation is one that we will use when we're dealing with capacitors. The other way to look at this equation that may be easier to do is how much charge can a capacitor hold? Well, that's going to be equal to the voltage, or sorry, the potential between them, the voltage, times the capacitance of that. I always like to have equations that don't have the dividing in it because it's always easier to remember these for me, but however it works for you, they're the same equation. Looking at, let's rearrange the equation in the third way. It can be CQ is going to equal Q over V, which is going to be in units. That's going to be a coulomb. Y'all still see this? Yes. A coulomb per volt is the charge, or is the unit for capacitance. We have another term that we'll use for that. We're going to call that the farad. That's in the glare. There you go. So the unit of capacitance is called the farad. It is abbreviated capital F. All right. So when you look at capacitors, you may see microfarad, oops, slide that back over. microfarad capacitors. So that's 1/1,000,000, 10 to the minus 6, 1/1,000,000th of a farad. You may see some millifarad capacitors. If you look on some of those big cylinder capacitors that people stick in the audio systems for their big boom bass in the trunk of their car, you will see this unit on there. Now you know what it's measuring, or what it's relating to. It's the capacitance of the unit of capacitance. So don't worry about all of it. Basically, it's just a number that describes the capacitor is all you really need to worry about in this class. So an application of capacitors. So a capacitor is a way of creating a electric potential that's localized to a very small place. We don't have to have these charges floating around, freely moving. We can like have a little cylinder in our hand that we can make a potential difference across an electric potential. All right, let's get this out. I'm going to leave my picture up for just a little bit. Actually, look at that. My board is starting to need a new eraser. Let me draw my wire back again. Ooh. All right, so when a particle travels from the negative plate, so here I've defined this is negative and this is the positive plate, just to make it nice and bigger to see. When a particle travels from the negative plate in a capacitor to the positive plate, it experiences an increase in electric potential. If it moves the opposite way, it experiences a decrease in electric potential. So you can very much think of this as, let's see, if I turned it sideways and put all the minus ones here and all the positive ones here, you can think of this as the top of a hill, okay? And I'll just do half the hill. So it increases as it goes to the positive. That should make sense off everything else that we've talked about on electric potential and moving from negative to positive charges and so forth and so on here. But that is an important thing that you need to worry about. And typically they will not travel through the middle here. They will come all the way around here. Maybe they're hooked up, you know, to a light bulb or something, in which case they will actually travel the long way around to get there, if that makes sense. All right, so we've got an example problem. How are we going to do this in real world? Why do I care? Why should you care about this? What's going to be on the test? What's going to be in the practice problems? So let's work on a practice problem, which means I need my board and I need some space, and it is 108, and we are theoretically done at 1:30. Let me see how we're doing. Hey, we're actually, we're going to be on time. Cool. So a freely moving electron, it gives us a mass, it gives us a charge. It starts at rest, traveling from the negative plate of a certain farad capacitor to the positive plate. How fast will it be moving, assuming the capacitor has so much stored charge on it? Wow. Okay, so we have, we'll do it this way. We have a freely moving electron. Let's do it here. An electron. The electron has a mass. You know, I don't need the E. It's only mass we're talking about today. The mass is 9.1 times 10 to the minus 31 kilograms. 10 to the minus 31 kilograms. That is the mass of an actual electron. Obviously, that is an extremely tiny number. Its charge on an electron is minus 1.6 times 10 to the minus 19, if I remember correctly, coulombs. Yes, correct. Starts at rest over on the negative plate. It moves, oops, and we have the capacitance. I think they do the C sub Q so that the C doesn't get confused with coulombs. Otherwise, normally I just use C's. Of a 3.1 times 10 to the minus 6 farad. 3.1 times 10 to the minus 6 farad capacitor. So that's the relevant number there. How fast will it be moving when it gets to here? So we, oops. we also have one more data point. The capacitor has 0.55 millicoulomb of charge. So 0.55 millicoulombs, which is equal to 0.55 times 10 to the minus 3 coulombs. And yes, again, I know that's not proper scientific notation. I don't care. It gets us the right numbers. At the end, when I give an answer, I want it in proper form of stored charge. So basically, we need to look at the energetics, so the energy of the situation. If we're asking for speed and they gave us mass, they're probably going to give you kinetic. You're going to have to get to kinetic energy. To get to kinetic energy, you have to figure out the potential energy to start with. So we're going to, those should be some clues as to how you're going to work that problem. So again, starting off, we're going to have total energy before equals total energy afterwards. Energy initial equals energy final. That's going to be potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. Actually, you know what? I'm going to do this in reverse so I don't have to flip things around anymore. Total energy final is equal to total energy initial. There, that'll save one step because I'm lazy. Okay. So we know that initially there is no kinetic energy. It is at rest. At the end, we're probably going to have, some of both, so we probably should leave that in. So let's see what we end up with. We're going to end up, I'm going to redo this again where kinetic energy final is going to equal potential energy initial minus potential energy final. Oh, wait a minute. We've got an equation that talks about the change in potential energy, don't we? Let me go find that one again so I can write it the same way they do, mostly. So this is really the change in potential energy. Cool. That means, actually, this is the minus change in potential energy because really it should be final minus initial. Let's do this. Just to be crystal clear on this, this is going to be minus potential energy final minus potential energy initial, which is going to be equal to minus the change in potential energy. Because it's always final minus initial to get the change. Therefore, this is minus that. Well, potential energy, we've got the change in potential energy. Equation they've given us, 14.3, is going to be equal to Q times the delta V. So in this case, taking this up here, this is going to be keeping that minus sign, minus Q delta V. Cool. Well, what is V? V is going to equal, oops, hold it. Yep. Making sure I'm on the right track with what they're doing too. So where's the best way to do this? Can't really move it. I'll just have to stick my head in the way. So the potential difference, I know they just use V, but it is a potential difference. So we can use the delta V terminology there, is going to be Q over C, or the amount of charge stored here divided by the capacitance. We have those two numbers, so we're probably good here. That means that this equation, taking this down here, we're going to have minus little q times Q over the capacitance. That's going to be the change in potential energy. I think we're now at a point where we can start plugging some numbers in. Actually, you know what? Let's not. Let's do one more step. I'm going to rewrite this up here so we've got it in one spot. The kinetic energy final is going to equal minus Q big Q over CQ. But this is 1/2 mv squared, which is going to equal minus Q over CQ. If we multiply by 2 divided by m on both sides, we're going to have v squared is going to equal minus 2. Let's see, 2 over m, yes. Q over MC Q, and then we're going to square root both sides. Get rid of the square. And that's what we're going to need to plug in. Where's my eraser? Get rid of some of this, so I've got room to come back over here and plug all these numbers in. All right, so the velocity is going to equal the square root of minus 2 times what is Q? Minus 1.6 times 10 to the minus 19 coulombs times Q on the capacitor, which is 0.55 times 10 to the minus 3 coulombs over mass, which is 9.1 times 10 to the minus 31 kilograms. Oops, wait a minute. I missed a K somewhere, didn't I? There's got to be a K in here. Where did I miss the K? Oh, wait, no, because capacitance has a weird value. Okay. Farads, yeah. That's times 3.1 times 10 to the minus 6 farads. And again, I'm going to pause here before I plug everything into my calculator. I want to make sure I didn't screw something up. So I'm just going to take the units here. I'm going to do square root. We've got a coulomb times a coulomb over a kilogram times a farad. That doesn't look really useful to me. So let me go back and let's look at what a farad is. A farad is a coulomb per volt. So we can at least do this coulomb per volt. That helps a little bit. I'm going to actually flip this volt up on the top now. What's a volt? Wait, where are we looking? Kinetic energy, we're dividing a mass. I've got to have a mass in here. Where's the kilogram going to cancel out? Have I left something out? I feel like I've left something out. Well, let's keep up with it and see what we got. Volts. Go back to the end of the volts because I don't have that one off the top of my head recently. Potential difference. Volt. So a volt is a Newton meter per coulomb. Yes. So a volt is going to be a Newton meter per coulomb. That's where I want to be. So we're good. Oops, we're in a glare here. There you go. So the coulombs cancel. We're left with a Newton meter. Well, a Newton is a, I'm going to leave that meter. I'm going to do meter newtons. A Newton is a kilogram meter per second squared, right? So let's put the second squared on the bottom. We're going to have second squared, kilograms cancel, meter times meter, meter squared per second squared, square root, we got meters per second. Great. That means all my algebra up here is probably right. Always good to double check with the units because they'll get you. Sometimes you have to go through a little bit. That one, I apologize, was so cumbersome. All right, let's plug those numbers in and see what we end up with. I've got a, let's see, Q, big Q is plus. Okay, so a minus, so we end up with a plus. That's a good thing. 1.6 E19 minus enter 2 times 0.55 E3 minus times. These are some very, very small numbers. Now we do 9.1 E31 minus divide, gets us back to a bigger number. 3.1 E minus 6 divide. And then we take the square root and hopefully, how many digits? 2 digits. So we're going to I came up with 7.9 times 10, 1, 3, 4, 5, 6, 10 to the 6 meters per second. Wow. Oops. Double wow. The reason why I say wow is that's a substantial percentage of the speed of light. I mean, it's not, I guess, that much. It's still slower, but it's fast. Let me flip back over. Which page were we on? All the way to the end. 8 times 10 to the 6 milliseconds. So they got 8 times 10 to the 6 meters per second. So I'm going to call that close enough. And for your parents who are looking when they're grading your test, if everything we went through was the proper procedure and we got this instead of this, it's okay. I like my answer better than theirs. I'm willing to bet they rounded somewhere, probably because they plugged numbers in earlier. And because you plugged numbers in earlier and then you had rounding here times rounding here, you're going to end up with something that, again, it's the right answer, but it may be a little bit off. That's where a little grace comes in on these things. And now I really, really hate that they still have this last part in the chapter because your TV does not work like this. How many of y'all actually have old screen, big fat TVs? Hey, yeah, you can send me pizza any day of the week. Any brand, I don't care. Pepperoni's amazing. There's my eraser. There's my eraser. Do any of y'all have an old style TV or computer monitor, one that's not a flat LCD panel, one that's more than 3 inches thick in your house? Not anymore. Nope. I think we still have one. It is not in use, but that's because I collect old electronic junk. I will say, if you have one and your parents will let you take it apart carefully, and I mean carefully because there's a glass vacuum tube inside that can shatter and do bad things. It might be interesting and educational to do so. Obviously, check with them first. But basically, and they've got this little picture inside in the book. It's going to kind of look like a bit of a flashlight. I got the wires coming in the back. Okay, so what kind of happens here is, well, let's do this. I don't like that. Let's do one here. I'll have the back end there. So we've got a couple of positively charged plates here. And essentially the back end of this, so this is the screen where, you know, you've got a little kid sitting really close up, you know, watching, you know, Bob and Larry on the TV show with a big old stupid smile on his face because he doesn't realize he's irradiating his brain. All right. Parents, you say, don't sit so close to the TV. I'm sure your parents probably still do. And there may be other reasons not to. But these days, it's not quite the danger as it was when I was a child. So if your parents say don't sit too close to the TV, it's probably because their parents grew up telling, or they grew up having their parents tell them that, because there really were real safety hazards. And I'll show you what those are. Essentially, this part of it was an electron gun. Some of y'all may be familiar with rail guns, where they take like the little metal discs or whatever, and a magnet and a magnet and a magnet, and they use magnetics to speed those things up, and they can shoot them up. So they can actually almost liquefy the metal when it hits the air. It's going so fast from the friction of the air. Those things can punch through, like, you know, the steel armor of a battleship and things like that. Some sci-fi movies have stuff like that. So yes, it is absolutely a household radiation cannon. Have fun with that. Don't harm your siblings without your parents' knowledge, at least. So there's a little thing here that basically emits electrons. There's a hole in the middle here and a hole in the middle here, and then there's some things here that focus it. So an electron gets generated back here. this plate is positive, the electron is going to accelerate towards the positive plate because opposites attract. It's going to start going faster. It's going to hit the hole. And normally, it might come back around and hit it. That's why there's another plate here. And so it gets past that one and goes, oh, hey, I'm going to go faster. And he eventually goes fast, fast, fast. And so this starts spewing out high-speed electrons coming out the front. Now, yeah, right. So that would just produce like a dot on the end of the screen. And y'all may have seen like old time movies where they show a TV turning off, and when the TV turns off, all of this, the picture kind of zooms down to the middle, and you get a bright dot in the middle, and then it fades away. And so that's what happens is as all the directional controls, which are right up here in front, shut down, that electron beam's still going, and it comes down to the point, and then it fades off. Well, on the front surface of the screen is a phosphorescent material. If like you shatter it open, there'll be very probably some sort of like powdery substance on it. I think maybe they use other things. Think of like a fluorescent light tube. You've probably seen those shatter, that white powder inside a fluorescent light tube, which is full of mercury, so it's really bad for you. So you don't want to mess with it. But that is a phosphorescent material. So it gets hit with the electron, absorbs the energy, and then re-emits light in the visible spectrum that you can see, usually in red, green, or blue. They've got the little pixels tuned to that. So how does this work? So the electron goes and hits the thing. It makes a flash of light. You see the flash of light. How does it make the picture? Well, there is a series of plates here. There's actually two this way and two this way. It's kind of hard to draw from this angle. So I'm going to draw front screen. So here's your old time TV, cathode ray tube. Cathode ray tube. Cathode rays are rays that come off the cathode, the positive point off of this, which means they are electrons, and it is a tube that is evacuated. There's no air inside, very little air inside. And so the beam comes here. There are plates here inside and plates here. And what they are is they are magnetic plates. And so they will flip from here to here to here to here, stronger and weaker, and they will direct the beam. So if a charged particle goes through a magnetic field, it's going to curve, okay? And so this creates a magnetic field here that causes, let's just do the vertical ones, it makes the ray bend up and hit that point, or bend down and hit that point, depending upon how it's done. The sideways ones work the same way. So they will go left to right. And so the picture on your TV screen is actually this single beam drawing out left to right, top to bottom, a picture until you get a picture drawn up in originally black and white, later color when they were able to fine tune them down to those red, green, and blue dots in there. And then it repeats itself and it goes, and it draws picture over picture over picture over picture. 60 times, 30 times per second, multiple times per second, depending upon what we're looking at here. So if you look at a TV screen on a TV screen, they may be out of sync just enough, and that's why you see those kind of black bands kind of moving down, is because they will be out of sync. Yes, I'm positive. I have to look at these jokes now. I'm pretty sure all of this gets recorded in the live stream too, so everyone will get to see, what all you've said, if that helps. So your jokes will live on through posterity. We'll find out when we watch the actual video later. And so you get this picture. That's awesome. It was amazing technology at the time. Again, the problem is you've got high speed, fairly highly energetic particles streaming forward at your face. Yes, they're being absorbed by this mostly, and then re-emitted as light, but there is still some level of increased radiation coming across your, to your face and your eyes and your brain and your skin and everything else, which is why it's probably generally not good to sit really close in front of one of these for long periods of time, like growing up every Saturday morning, which may explain a lot about your parents, just saying. All right, what else do we have? I think they do. Yep. And it does go on to say LCD TVs are substantially different. There are some similarities, but they don't operate in this way. So they should be a lot safer to sit up close. You might have like eye strain problems or things like that, but as far as the actual radiation, shouldn't be as big of an issue. It is 1:30 on the dot. I'm amazing. Does anybody have any questions now that I can actually look at the chat before I go back through everything that was in the chat once we're all gone? Yes, the last class was not uploaded to YouTube because I recorded it. It wasn't automatically recorded, so I've got to get that to them, and then they will upload it to the YouTube. Let's see one. Okay, what was the other one? What's the high-pitched noise? Oh, the high-pitched noise they make is going to be some of the I'm not sure exactly why, but I can hear them too a lot. The components are, because sound is a physical vibration, very likely it is coming from the because a lot of electronic circuits can make those high-pitched whines. There are things that are vibrating very, very quickly here, 60 hertz, et cetera, for the electric stuff. I would be willing to bet that it's small movements like in the magnetic plates or something else, but there are, like when I was a kid, I could walk into a particular grocery store where I lived, and I could hear this high pitched whine. It was like a dog whistle. It was extremely painful. I think I did that to y'all in class. That was just me getting even because I can't hear it anymore. And so yes, they do make a high pitched. It's probably something relating to the electronic circuitry. It could be related to some actual physical vibrations from like the magnetic, the magnetic plate switching on and off and on and off. It's going to slightly move other things as well. So I haven't actually done the research to see where that is, but that would be a good thing to figure out. Were those all the questions? Have I missed one? Somebody said there was one above, but I think that may have been the high pitch noise. That was yours. Okay. Somebody, if I missed one, please type in the chat again, or I will try to scroll here as I'm just getting all the puns and jokes. So I'm hoping there wasn't one up, further. Okay, cool. All righty. So good luck. Everyone make sure your parents have your stuff in and graded to Ms. Ryder before end of day today. I sent out email with all of that, I believe. If anyone has any problems, if any parents have any questions, have them get in touch with me. Email should be fine. Just make sure like SIM or physics or something is subject line so I can pull it out of all the junk I get. And I will be online Tuesday night again with parents who have any problems, grading papers, tests, whatever. I guess no tests this week. All right. Good luck, everyone. Stay safe, stay alive, wash your hands. Everything's fine. It's fine. Where is the end meeting?